So this is the second part to my proof by induction video. In the last video we went over proof by induction for powers of matrices. So we proved that, we proved that, excuse me, A, B to the power n is equal to A to the power n, B to the power n for natural numbers n. So this is powers of matrices problems. And sometimes it will be a bit more complicated than this, but essentially the question is asking for you to do proof by induction. So hopefully they don't make the matrix too complicated. So next one will be, so this is powers of matrices. So the next one will be sums of series. So let's do some sums of series question. Let me think. So let's have, this is show that this is true. Sum from k equals 1 to n is equal to n times n plus 1 over 2. So these are the triangular numbers. So let's see, how would you prove this? Same steps as before, so let's write down the steps. Base case, induction hypothesis, inductive step, and conclusion. So base case would be, so we would prove this for natural numbers n. Base case, sometimes a base case may not be n equals 1, it might be n equals 9 or something, but base case, in this case is n equals 1. For n equals 1, the right hand side will be equal to sum k equals 1 to 1 of k. This would be equal to 1. Now 1 is equal to 1 times 2 divided by 2, and this is equal to 1 times 1 plus 1 divided by 2. And this is clearly the left-hand side. And so you can give that tick. In fact, the little box means end of proof, so I shouldn't write that down. But you just give it a little tick to show that n equals 1 is true. So let's see. Now we need to do write down the induction hypothesis. So induction hypothesis. What is the induction hypothesis for this question? Well, I can't say suppose it's true for some number k, because we've used k as a running index for the sum, which makes it kind of annoying. Let's suppose it's true for some number a instead then. So let's call this p, like we did last time. Call this p, or maybe predicate. P, and suppose P is true for sum for not for sum, for n equals a or something. Suppose true, the p is true if n equals a. So in the induction step, inductive step, we need to show that it's true for n equals a plus 1. So let's write down the sum to a plus 1, k equals 1 over k. This is equal to, well, it's equal to sum k equals 1 up to a of k plus a plus 1, right? We're just taking the last term and writing it outside. From the induction hypothesis, we know what this is. It's equal to a times a plus 1 over 2 plus a plus 1. And this is from the induction hypothesis because we assumed p is true for a. Now what we have is that we can actually factor these out, and we have a plus 1, a over 2 plus 1, like so. And we can now factor out a half from this. So we have a plus 1 times a plus 1. I'm going to write it like this, plus 1, but it's actually just a plus 2 over 2. But this means that thus p is true for n equals a plus 1. Okay? And now it's time for the conclusion. Since p is true for n equals 1 and p is true for n equals a, implies p is true for n equals a plus 1 by the principle of mathematical induction. P is true for all n in the natural numbers. End of proof. Okay, and that's about it from me.